Mercury is a big issue, and it's a big concern because there is an ongoing ban of mercury worldwide. I think you know about it. So slowly it's coming, and I will show you the content of this presentation. More or less tells the characteristics of the mercury, how is it, how does it appears on the Earth, where it appears on the Earth, the emissions and the countries with potential issues with mercury. And then we go through the sources of the mercury for cement and what are the transformations of the components inside the process, how it does, how mercury behaves on preheated precalcinic kilns. I skipped the long kilns because I think you don't have it here in India, so I just skip it now. Then some wordings about mercury control and mercury abatement techniques. So mercury is very mobile. It's only liquid at the ambient temperature. The most common forms are the cinnabar, not soluble, not volatile. But in the pyro process and on environment, 100% of the time, it's very volatile on the hot sections, and on the exhaust, 95%, 20 is on the exhaust. It is volatile. Mercury chlorides, they are soluble, and they are between 5 to 80% on the exhaust. They are also particulate bound, oxidized, and they are soluble. On the hydroxide, the mercury hydroxide on the concrete, it precipitates as long as the pH is high. So it is there. If we have the pH is high, then it precipitates. And the methyl mercury is the one who is, let's say, the healthy concern. Mercury, it's on living organisms. When it's present on the food chain, then it's really a problem because mercury is bioaccumulated. It's very well known, causing disease, neuro disease. We have this Minamata case, you know well.
I have one question on the previous slide. Here it is mentioned that HgCl, it's soluble, it's 5 to 80% in exhaust gas. What controls this limit? Means
yes,
whether it will be 5% or 80% or something in between?
It will depend on the process conditions. We will show later on how is it the split of the mercury, the oxidation, and the speciation of the mercury on the cement process. Mm-hmm. So if you wait a little bit so we get there.
Okay, sure.
Okay, mercury on Earth. Mercury is 50 ppb on earthly crust. It's how mercury is also linked to volcanic activities. We will see how is it the behavior of the mercury release to the atmosphere, then to face waters, and how does it participate on the background levels of the mercury, because it's once it's on the atmosphere, it's traveling all around. And here you can see more or less the atmospheric mercury deposit. So we have seen on the pre-industrial areas, the green areas, then you can see the volcanic releases of the mercuries on the blue lines. And then you see it completely the increase of the mercury when we started to have the industrial revolution. But here is the gold rush. This is the mining. It's also when we have a lot of mercury release, because it's, you know, for extraction of the golds, they use a lot of mercury. Then, as I just mentioned, for the mercury roadmap, what are the countries that may face problems with mercury emissions? and India is there on the orange and red light, if I'm not mistaken. So there is, and Europe, you see, it's completely red, or most of the majority are in red. And that's why this is one of the reasons why it's starting to limitate the mercury emissions of the industries. Now it comes to Europe, one topic that I would just mention for you as an information, which is called REACH, which is regulating the products, the, let's say, hazardous contents on the products and the chemical. It's regulating the chemicals on the products. The minor elements are there. The mercury is also there. And they started to be reported and to be followed up. So the regulations are becoming more stringent, and the follow-up and the limitation of this component, it's becoming more and more tough. Most of the countries who has problems with the mercury, it's because they have they use a lot of coal. They have the power plants are the main emitters of mercury. So the coal power plants are the ones who are the black spot, let's say, of the mercury releases on the atmosphere. On the cement industry, we also have seen that we have a significant contribution. It can come from the raw materials, but also from the fuels. So if we have coal with a lot of, we will see more or less the range of the levels of the mercury on the material. So you can see there. It can also come from the limestone or marl, from the clay or shale, also from if you started to use alternative raw materials, foundry sand, iron ore, pyrites is also there. So you see that they are, they can be everywhere. Also fly ash, I didn't mention before. And on the fuels, the range on the coal, it's around from 0.1 to 1.3. And we have cases, or I know cases where the problem of mercury was not coming from the raw materials, that is sold on the literature a lot for cement industry, but coming from the fuels. All these fuels that we have it, solid shredded waste and waste-derived fuels and all this that it's coming from industry or from the municipal solid waste is also having a lot of mercury inside because it's everything mixture and we do not know what is inside exactly. And it can be really an important source of the inputs of the mercury into the system. So how it occurs, the transformations of the mercury inside the process. So we have the combustions, the heating, and then we have the metallic mercury being released and all the others, SO2, SO3, nitrogens, and chlorides. And then here you see on the right side of these slides, this is what you were asking, right? All the species that are the oxidations that mercury is being oxidized with the gas composition on the process. So the metallic mercury on the hot areas, when it's there, it goes straight through the stack. And it can also be bound on the particulates, and it will be more or less on these forms. This is more or less how is it representing the cycle of the mercury. So mercury enters into the process via raw materials or via fuels. And as it is volatile, we have seen that there is an external cycle creating between the upper stages of the preheater plus the raw mill, the filter, and coming back on this on the red curves that you see there. This is the external cycle, so we could say. And from the fuels, you have seen that the blue area there, where we can have some mercuries that are coming from the fuels, having this create an internal, so we call internal cycles for the mercury. So one way to, when we want to control the ways, either from the inputs, either if we had the chance, we replace the raw material or the alternative raw material, there is a problem, or the fuel that has a problem. From the process control, we have seen on this that we can do dust wasting, that I'm going to talk a little bit later. So there is the dust wasting, where you extract the dust from the filter, and also when the raw meal is off, because when the raw meal is off, the mercury emissions goes up to the head. So if and it's a good time to do the dust waste collection, because the dust bounded with the particles, you trap them and you how to say this? You purge the systems and you reduce this cycle of the mercury creating between the preheater and the raw meal. Another way that it's not here on the process control is to keep the temperature of the exhaust gas of 140, because when you on the raw meal is off, the mercury. The thing is that in Europe the mercury is monitored continuously. So the plants there, they have to keep the levels of, in Germany, of 28 micrograms per cubic meter daily average. So they have to keep this limit. And to keep these limits, there are some also the temperature, optimal temperature that the system has to operate. So the inlet of the filter, you have to be around 140 degrees, and also to do this purge. If this is not enough, then you have to go for activated carbon. Activated carbon is also mentioned in the BAT document. It's very effective. We put it some grams and it's gone. It's really, really effective. We have seen also on the wet scrubber that there are some mercury trapping on the wet scrubber. And also on the dry injection system, there is also part of the mercury that can be extracted through that. But we also saw that only the oxidized form of the mercury are trapped, are being captured by these techniques. The metallic mercuries go straight through the stack and being released into the atmosphere. There is one study mentioned that we can, so if we want to reduce the mercury, so to convert the element of mercury into oxidized form, so you can capture this oxidized form through a carbon addition with some catalysts, but I cannot really give you what is the efficiency of this. I think this is just an experimental phase for the mercury. This is what I was telling. So the gas, the controllings, so the gas temperature should be kept below 140 in continuously. And here are some remarks about the thermocouples installed in front of the dust installation. So you have you are sure that you are measuring the temperature correctly. The locations of them has to be carefully chosen because of leakage, because of all the others, it is written here, fresh wear flaps, broken composite, that can influence and can give a wrong reading of the thermocouples and not really being effective for the setup of the control system to keep the mercury trapped into the system.
This 140 is for metallic emission or for normal process absorption?
No, this is process.
Process.
Process. So this is what I just mentioned. Before, the dust removal. So it's helpful. It reduces you keep the system running, and you are not releasing very much mercury on site. But it can be expensive because you have to dispose this waste, because then the dust you collect, it's considered hazardous waste. And in Europe, the cost of disposing this kind of material is around 25 euros per ton. In some countries, it is allowed to use this dust as a filler on the cement. And so some plants also are using this on the cement production. The emerging techniques, the polishing baghouse, I think this is well known from Gore, but it's also very expensive, 20 millions. And also the plant has to install additionally the filter, the fan, and also for the solvent installation, also it's a completely new set to be on top of what is existing. When I mentioned about the activated carbons, we have used in one case in one plant lignite coal, if I'm not mistaken, Harad, to Germany, lignite coal. That was also it was very effective, it was not activated carbon, it was much cheaper, and it was also
in addition to normal dust, this baghouse will collect mercury also. We are having normal baghouse, and if you compare to this polished baghouse, so the same baghouse will, if it is a polished baghouse.
And this is what I'm telling. We had a normal baghouse, and we just put this lignite coal, and it was also very effective. The problem is that we had also a bypass, so it was just treating one side of the emissions. The other was untreated.
So
but when you do it just before and you don't have any bypass on the circuit.
This baghouse can control dust also and mercury also simultaneously.
Yep.
All the things.
This one is CPAC method. The thing of this, it's the promotion of this solvent is because it can be used on the cement and also as a concrete filler. They say that there is no impact on the qualities of the finished materials. It is injected 450, so this would be on the upper stage of the preheater.
Excuse me, ma'am. Polishing baghouse, what is the sorbent which you are using?
It was activated carbon on the polished baghouse. It's called BPAC. It's also a normal activated carbon. Okay. The example I just mentioned, it was the lignite coal. It's nothing to do with the polished baghouse. It was just one simple alternative measure taken in one plant, and it worked. This is what I meant. Okay, this new setup here, this other setup here, you saw it's much cheaper than the other one, 750,000 euros, but the reduction is not so it's not so efficient, but I guess it's because of the forms of the mercury. It's just taking care of the, treating just the oxidized species of the mercury. The CPEC, the CPEC,
I cannot translate what it really means, but these are trade names of what is the name of the company? Albemarle is
Yeah.
the name. And I think BPAC is the bromide. It's activated carbon with
enhanced with bromide.
enhanced with bromide.
Yep.
Yes, as an oxidant, because we have said the problem is that the elemental mercury is not reacting, so you need an oxidizing reagent. They put bromide inside. And CPAC, I don't know what they do and what is the point, but CPAC, they treat it in a way that you can use, that it's also active in very high
It's not
temperature.
harmful on the concrete. But the bromides, it's because it is said that the halogens, they are acting like a catalyst, so they are improving the absorption of the mercury into on the activated carbon. And when you have this bromide enhanced activated carbon, you have a more effective absorption. Sorry.
Where will you inject it?
Sorry?
At which position we have to inject? Where we have to inject this? Inject the 450.
The CPEC is on the upper stages of the preheater, is at 450 degrees, the injection point, and the other point is on the other side. It's around a scale up. It's a scale up to 260, so you have before the filter. So you have some range up to 250. You have more, degrees of freedoms where to install it. It works on this up to 260 degrees.
I mean, when you ask where to inject it, it has also to do that you know the situation with Rommel stoppages. You increase, when the Rommel is running, you have 100 degrees, no problem. When you stop it, you are at 200 degrees, and then you have an emission of mercury very often. And so then you can use this high temperature BPAC at the same point, but at higher temperatures. This is also very important for this material.
These are the tools for mercury. And the last one is about the heavy metals. Where I'm going to tell you more or less, there are some nomenclature about trace elements and heavy metals. The most relevant metals on the cement process, the chromium, lead, cadmium, thallium. What are the source of the metals, how they are classified, their behavior, and some experiments that has been done on concrete about the leachage of the metals. So where they come from, where they go. So we have seen all these green elements noticed on the periodic tables. They are trace elements. They are essential for us for living. They are in everywhere. They are in our food, and then they are. We have to take it some low daily intakes doses, and they can be found everywhere. But there are some trace elements that I have remarked to you. So the most important, the most volatile one, the mercury is in there that we have just talked, the blue one, the thallium and cadmium, which are what's so-called in the same industry semi-volatiles. And the other ones marked in black, the ones that we have to monitor. And for the sake of the emissions on the cement industry, they are considered as a heavy metal, a so-called heavy metal. The chromium itself is one of the least volatile metals of concerns. It is the main concern is because the chromium if it goes through the clinker and if we have the chromium 6 on the cement, we have a problem of on the skin. We have a disease problems. This was found out, and there are some regulations in Europe that the plants has to keep the levels of the chromium in the cement at 2 ppm. Because of the workers and also for the people who works with the products. The main sources of chromium on the raw materials is slag and iron source, and from the fuels is coming from the coal, oils, and tires. From the lead and cadmium, they are no volatile metals. There is lead is known for this for the health effects causing on the nervous systems. The main source of lead is also coming. All of them is coming from raw materials and fuels. Cadmium can cause very severe health problems and is also being considered carcinogenic. And the main sources on the cement industry of cadmium is coal, plastic waste, and biofuels. And thallium is one of the metals that exists also and can be combined with several other elements. The oxygen, sulfur, and halogens is the same volatile metals. We have seen that it's highly toxic. The main sources of release is not cement industry, but I can tell you one story, not very happy end story, happened in Germany in a cement industry old time in the 70s, and it was about thallium, because thalliums get into the circuit, into the process we are going to talking about, and he get enriched into the process and being absorbed on the dust particles. And it was an ESP, and when there was CO trips on the ESP, there was an explosion of the ESP, and all this dust was released everywhere on the surroundings, and it's more or less killed all the species around. That's why it's one of the concern metals that we have to keep an eye on it. And for the, let's say, daily-to-daily operations, for example, you have here in India or anywhere, I have been working for some periods to set up the maximum level that the plants would have on their filters, because when you do maintenance, for example, on the filters, if you have a high content of thallium, and the people who are working and doing this kind of works, they are exposed there to the dust. And as it is highly toxic, so can be also a safety issue that you have to address in the cement plants. And it's found on the raw materials and the fuels. These are the range of the heavy metals in raw materials. It's a table from VidiSat, so you can see it, more or less, what are the ranges of the levels in the clay, in the limestone, the raw meal, and the clinker. And there is a very nice tool of VidiSat. I'm not sure if you know about it, where you can use trapping coefficients for the metals and determine more or less the compliance of the plants when you have new inputs, new materials coming to the plants. If they are coming from the raw materials or if they're coming from the fuels, you have just to do the analysis as like a pre-test, not just doing the analysis, but the income, and you can estimate how much it will be on your emissions in the end. On the fuels, Coal and pet coke can have up to 4 ppm. But the influence of the thallium, it's, as I said, it's very low. It is there, it's a risk that is there, but nobody talks about it. So we have the classification of the trace elements, so we say where they are going to be the high volatile elements, so mercury on the gas phase above 90 degrees, thallium above on the upper stages of the preheaters, and the low volatile elements cadmium and lead on the bottom of the stage of the preheater. So more or less, and the non-volatiles, this means that all of them goes through and it's trapped on the clinker structure. But there are some question marks here. See, for the antimonium and tin. Is it tin? How do you say? Tin, huh? Okay, so we see very little mercury on the clinker. It's everything on the other side. And it will be oxidizing with sulfates, and chlorides also help to keep them on the other side of the process. Chromium, very non-volatile metal, and it's going through, and we have to take care about the mercury, the chromium 6 on the cement. The lead and cadmium, both very low volatiles, and there is here that there is these accumulations of these no volatiles into the kiln inlet and the bottom stage of the preheater. But most of the lead and the cadmium leaves the systems with the clinker. The thallium, which is the same volatile, is the one I said that there is this recirculation of thallium on the filter, the accumulation of the thallium on the filter. On the upper stages of preheaters and the filter. And then just a remark on the end that the removal of the dust from a kiln bypass, it will be less effective to remove thallium, of course, because it is there and not down, instead of the removal of the cadmium and lead. So more or less is the way, how is it showing the behavior of the volatile, the tiles on the clinker process. So you see it on the light blue square, or where is the thallium accumulation. So in between the preheater and the main filter. And for the non-volatiles, you see it, it stays on the bottom of the preheater. It's everything kept there. And going through together with the clinker. How they behave on the clinker and concrete, I think Cornelia, that was here last time, I think she had presented this to you. So more or less, they are adsorbed on the calcium silicate hydrate gel. They get fixed on the crystal phase of the concrete, and then create salts on the silicate hydrates. There is the creation of silicate hydrates and basic calcium salts. With very limited solubility. So this means that when we do, and this is what is coming to the concrete release rate, so you can see it on the first two columns, the cements, and the cements, the type of cement used, cement 1 and cement 3, and that was used to do this concrete. And on the last three columns, you see more or less the standards of the water. So for spring water, for natural mineral water, and for regulatory limits for drinking water. So if you just have a quick look on that, you see that the releases of the metals on the concrete, should be not a concern for us. This is what it means. Oh, yeah. It's just the way how to represent them. So the limits, this is just a chart of one of the testings of the heavy metals after 200 days, how it looks like. So you see that there are not too much released. And the drinking water, you see that they permit, I think there is here, Mercury 1 and what's the other? And from the chromium 50. So that's why you cannot see it, because it's up to the limits on the drinking water is much higher. So it should not be a concern. And with crushed concrete, you can also see that is also not a concern. So from the concrete side point of view, maybe you have done these tests already. I do not know if you have already foreseen here this on the research center. This was the last slides. You have any questions for the? Is it the case that heavy metals and mercury will turn to be a concern in India, or how do you see it?
By which instrument you are detecting all these elements?
Sorry?
By which instrument you are detecting all these elements? How you detect?
I don't know how they did it. I don't know what equipment they have used it. I'm sorry. I can have a look and I come back to you with this. I come back to you with this. It's a very old study, but it's a very useful, I guess, for the sector. I can have a look on this study. More questions? So it's not a concern for India as well? I guess not. Yes. The recap. Yes. You are going to receive now.
Can you repeat the question, please, once again?
I asked it before if heavy metals and mercury is having the same levels of concern for India, for the cement sector, I mean.
Yeah, for the plants that are using the hazardous wastes as a fuels, for that there is a standard for heavy metals and mercury also. For rest of the plants there is not as such a standard.
Okay. So the plants who do not co-processing, they never monitor mercury, or do they have to monitor even if it is 2 times a year?
For the co-processing plants also standards are there, and in that heavy metals are incorporated.
But for the ones that do not co-process, they don't need to monitor. Okay. Okay.
In central India, the mercury has entered into the water table, and it is having very devastating effect in the district. Children are born with disabilities,
Yes.
and it is affecting the adult population as well. So yes, it is a matter of concern, and at this point of time I cannot recall the name of the district that is there. Very recently it was in the news also.
Yeah. No, that's why I asked it, because I understood that the
Yes, if that is
monitoring
the
the
question, yes,
requirements
it is
just
a
coming
grave
from the
concern,
corporation?
matter of grave concern for us. Elsewhere also in the country, there have been a few districts which have reported that heavy metals have leached into the water table, they have entered into the water table, and now they are affecting the children, the adults, and deformities, disabilities, and the adults also, they are taking up new diseases.
Mm. Okay. Yeah. Yeah, maybe we talk later. I have other questions.